Okay, so welcome back to another video. So today we have a improper integral from 0 to infinity of arctangent of x squared divided by x squared dx. So I did something similar like with the arctangent function specifically, and that was, the arctangent of x divided by x to the power ln of x plus 1 dx, and you can check that in the description below if you haven't seen it yet. That video is actually a little bit shorter compared to today's video, since a lot of the computations from that video was mostly justified from results that I already proven in past videos, so there was no point of having to redo the work again, since you can actually just look those for yourself if needed be. But because this is a little bit different, because for one, this is a lot lengthier compared to the aforementioned video. A lot of it really is just utilizing some special functions. Of course, obviously, you can see that this is not easily integrable just using your standard techniques used in a standard calculus class. So we have to fix some things up just a bit to the point where it's actually doable for our part. So I really don't want to give too much any spoilers on the steps, so why don't we actually just go ahead and jump right in. So obviously we would know that you can see that you can't really do any sort of u-sub. Maybe if you can try to do integration by parts, but I think that method will just make things a lot more, it'll make things a little more difficult to work around with it especially. So I think the easier way to do it this way. So let's first notice that we can actually define a function. So I'll just call this f of alpha, and we could set that equal to the same improper integral, except that the generalization is that we have that this is alpha times x squared, then divided by x squared dx. So I think it's also worth mentioning that the given integral, I'll call this capital I, we notice that if we actually just plug 1 for alpha, then we actually get our given. So just a little note that might come in handy in the future. So we could say that capital I is equal to f of 1. What I can do from here, let's actually take the derivative of both sides. So we have f prime of alpha, then that means I would actually have to take the partial derivative in respect to alpha of our function. So alpha x squared, then divided by x squared, then dx. Okay, and then you'll see that if you actually do this correctly by using, the chain rule here with partial derivatives, we'll get that this is the integral from 0 to infinity of 1, and then divided by 1 plus alpha squared, then multiply with x to the power 4th, and then dx. Alright, so now what we can do is let's actually perform a little u-substitution. So this might be difficult in trying to come up with some how to call a standard variable x. So let's actually call x to be the square root of tangent of t, and then divide that by alpha. So here we have tangent t, then divided by alpha. So what we can see is that if we just differentiate both sides, so dx is equal to, so you'll notice that we have 1 over the square root of alpha. And so I can actually factor that outside. So that's just a constant, so this is just square root 1 divided by square root of alpha. Then really we're actually just taking the derivative of the square root of tangent t, but that's really easy to see by applying chain rule, is that you'll get secant square of t, and then divided by 2 times the square root of tangent t, and of course dt. So now from here we can actually perform some substitution, well really the substitution, and just put things back to where it should be. So meaning we would actually have to calculate our new bounds as well. So here f prime of alpha, we have 1, then the over 2, then times square root alpha. We can move that outside of the integral. Those are just constants, not depending on t. So this is just written as follow. So now we have to calculate our new bounds. If we see that x is equal to 0, then we can say that the lower bound here, that's still going to be 0. Then meanwhile, we have infinity, so we could say that just from solving that t would have to be pi over 2 for the upper bound. Then if we just plug everything back in, so we have 1, and then 1 plus alpha square, okay? Then we just plug in our x back into here. That will be in terms of t, so now this is the square root of tangent t divided by alpha, then to the power 4. And then we just put back our the dt substitution, so secant square of t, then divided by the square root of tangent t dt. So that's nice. Now we can actually do a little bit of simplifying. So really specifically for the integral inside. So here, just going back, so f prime of alpha, I'm just rewriting things a little bit, rewriting things again. So same thing as here. Okay, 0, then pi over 2. Then what we'll notice is that we have 1 and then 1 divided by 1 plus. So this is still alpha square. Then we simplified what's in the expression in here, so we would have tangent square of t, then divided by alpha square. Then let's see, this is still the same thing over here, secant square t divided by square root of tangent t, and then dt. But you'll notice that the alpha squares cancel each other out if we were to perform the multiplication. And what you'll notice is that, and I'm going to skip writing this step, but observe that 1 plus tangent square t using some trig identities, that you can rewrite that as secant square of t, and they'll cancel from both the top and bottom. And so what we're left with is just 1 divided by the square root of tangent t inside of as part of our integrand. 0 pi over 2. Then we have 1 divided by the square root of tangent t. Now, we can actually write things a little bit further in terms of, our square root tangent t, because the following function we'll be using is actually a beta function by using, the sine cosine representation. So if so let me first put it out here like this. So pi over 2. So obviously, square root of this can be written as tangent t to the power negative 1/2. And of course, tangent t is the same thing as sine t over cosine of t. So therefore, I can write this as cosine of sort of 1/2 t, and then multiply with sine of the negative 1/2 power of t, then dt. So now let's actually write out some properties or formulas for the beta function that's going to be important to utilize later. So for some value for u and v, so beta of u and v, simply we know that for the integral representation with cosine and sine, that's written as 2 times the integral from 0 to pi over 2 of cosine of 2 to the power u subtract 1 t multiplied by sine of 2 to the power, or sine to the power 2 times v minus 1 t, then dt. And so let's actually focus on evaluating this integral. So here, or I wouldn't really say evaluating, because we could actually just substitute the b for, for beta in terms of that, not explicitly evaluating, in other words. So cosine of 1/2 t, then sine of negative 1/2 t. So if you solve for your parameters for u and v, you'll see that we have, so there's a 2, so I just divide this by both sides. So we have 1/2 multiplied by the beta function of our u being 3 over 4, and then our v being 1 over 4. So there, we can actually just substitute this back. So therefore, our new f prime of alpha is going to be 1 times 2 to the square root of the square of alpha multiplied by 1/2, then the beta of 3 over 4, then comma 1 over 4 with the, our parameter arguments. Now, another thing to note is that we can also use the definition of the beta function in terms of gamma functions. So I'll just use the same, put uv. In terms of gamma functions, can be written as gamma of u multiplied by gamma of v, and then all this divided by gamma of the sum of your inputs, u plus v. And I think it's also worth noting that eventually, if we do simplify this out, I think another important formula that we're going to need is Euler's reflection formula, which says that if we say gamma of u multiplied by gamma of 1 minus u is simply just equal to pi, and then divided by sine of pi times u. So I covered this video, I covered Euler's reflection formula before. I can actually put that in the link in the description if you haven't seen that yet. Going back to evaluating this part. So we have 1 divided by 2 square root of alpha, then multiplied with the beta, 1/2 beta. So I think it's worth noting that we need to evaluate this. So obviously beta of 3 over 4 and then 1 over 4. Okay, simply we just put this as gamma of 3 over 4, then gamma of 1 over 4, all this divided by beta of 3 over 4 plus 1 over 4. But in other words, we know that the well-known value of gamma of 1 is just equal to 1. So this can just be 1. And so the last thing we have is just beta of 3 over 4 then times, or excuse me, gamma, the 3 over 4 times gamma 1 over 4, then we can actually just use the property of the Euler's reflection formula and say that it's pi over sine of, so we'll see the parameters is 1 over u, so that, or 1 over 4, so this will be sine of pi over 4. Then we can see that just evaluate from that, we're going to get that this is just equal to pi, then multiply the square root of 2. Now from here, we just substitute this back in, so 1 over, so I'll put it like this. Let me put this in a new marker, or put this back in the same marker as before. So that would mean f prime alpha is just equal to 1 divided by 2 square root of alpha, then times pi times square root of 2. In other words, I'll write it like this, and then don't forget to multiply the 1/2, so really it'd be pi times square root of 2 divided by 2, but I'll put this as pi and then divided by the square root of 2. This is simply still the same thing. So now we're just about almost done. There's a couple things left we want to see. So if you notice that if I were to plug 0 for alpha, and if I plug 0 here, then that means f of 0 is actually going to equal 0. So that's actually another thing worth noting, and that's very important to use later, because what we want to do is that if we want to evaluate this given our given function, we would have to evaluate the definite. Well, we would have to integrate our generalization that was already derived. So in other words, I'll put it like this. So we have that I is equal to f of 1. And so what you see is that I can actually write this as a definite integral from 0 to 1 of f prime of alpha d alpha. So if I were to integrate this, then we would just have f of alpha evaluate from 1 to 0, which f of 1 was what we want to show, but you'll notice that the condition that we just imposed, that if we plug 0, we're going to get that 0, so we're just back to the beginning over here. So in other words, I'll put this as evaluating from, so I can factor out the pi over square root of 2, so that's just a constant, and then we're evaluating from 0 to 1 of 1 divided by 2 times the square root of alpha, d alpha, and it's actually easy to see that 1 over 2 times the square root of alpha, its antiderivative is the square root of alpha. Then all you gotta do is just plug 1 and 0, 0, 0 for there, and then 1, so it's just, 1. So therefore, the final answer is that it's simply just pi divided by the square root of 2. Or in other words, if you want to get rid of the radical in the denominator, you could say that it's just pi times the square root of 2 divided by 2, whichever way you want to put it. So, but there we have it. That's the final answer, written just like that. Maybe you might want to back it up just a tiny bit. There we go, that's better. Sorry about that. Just cropped out just a little bit, but there we have it, the final answer of our given integral. So yeah, that's pretty cool if you ask me.